Folks, in this video we're going to be discussing inverse functions again, but specifically through the context of the horizontal line test. Now you might be thinking to yourself, I've never heard of the horizontal line test. I've heard of the vertical line test, but not necessarily the horizontal line test. Okay, so let's just start with this. Okay, we've been discussing inverse functions. And I have a couple of functions here. We've got our quadratic function or squared function. And we have our cubic function. But essentially, let's go ahead and kind of sketch what we're talking about here. Actually, it would be much nicer if we could just see it over in GeoGebra here. So what if we had a function f of x equals x squared? Now, we've got our parabola here, and of course if you're familiar with the vertical line test, basically the vertical line test is concerned only with this. It's a yes or no question, and the question is this: is what I'm looking at a function, okay? And this is easily answered by basically answering one question. Does every x or every input in this relation go to one and only one output? And so previously, we could make a vertical line. How about we, oh, actually it won't let me do that. It's not a function. But we could make a vertical line basically anywhere on this graph. Basically, vertical lines go through one and only one x value. But if a vertical line can go through my graph, pass through my graph, and hit one and only one y value, then that must imply that every x value went to only one output. Now, the thing is, when we've been discussing inverse functions, okay, so inverse functions, we say the domain and range have been getting switched. So what this causes to happen is when we graph it, we see that it's reflected. It is reflected about this line y equals x. Now, I want you to consider all of the points on this original graph if they are reflected about the x-axis, and potentially maybe we could draw this. So we've got 0, 0 on the original, 1, 1 on the original, negative 1, 1. We also have 2, 4 and negative 2, 4. So So here are our original parabola points. Yay, that looks good. So if we were to find its inverse now, okay, so if the original is y equals x squared, then we'll switch the domain and range. That is, all x's and y's switch around and solve for y again. So radical both sides. We get y equals plus or minus radical x. So let's say, for example, we were to take, the original output 4. Okay, so 4 was at a height of 4. It should map us back down to 2. So we say y equals radical 4. We get plus or minus 2. I suppose I should write it like this: f inverse of x equals f inverse of 4, pardon me, equals radical 4 equals plus or minus 2. That is, on our inverse function now, and maybe I'll switch colors here, our inverse function, when we plug in 4, it goes not only to positive 2, but also to radical 2. And since we just got done having this discussion about the vertical line test, one might already see that our inverse function, I shouldn't call it that, is not actually a function because it would fail the vertical line test. But let's go ahead and plug in another set of outputs here. What if we plug in f inverse of 1? Okay, because 1, a height of 1 was one of our original outputs here. If we were to plug in an f inverse of 1, we get radical 1, we get plus or minus 1. So on our inverse function, we plug in x value of 1, we get positive 1 and negative 1. And then for the sake of time here, I'm going to put on 0, 0. Here is our inverse function. Okay, I shouldn't call it a function. But it is reflected about our identity function, y equals x. But what you see is this: our inverse relation here doesn't pass the vertical line test. It simply fails it, and it fails it miserably, okay? But I guess what I'm saying in this video is this: we could have been able to tell that before we even graphed or found the inverse function just by looking at or observing the original function. That is, if all of our original x and y points, okay, are switching their y and x values, then yes, they are reflected about this line y equals x. But, remember, to check for functionhood in the first place, we would have been using the vertical line test. And the original function passes the vertical line test, okay? But its inverse does not. So if its inverse does not pass the vertical line test, its inverse does not pass the vertical line test, then the original, think about this, would not have passed since it's reflected a horizontal line test. Ooh, I said that very, very deeply. Basically, if the original has a horizontal line that passes through it 2 or more times, then when we reflect it, or when we find its inverse, okay, it will not then pass the vertical line test. So the horizontal line test basically says, okay, if the original function has a horizontal line anywhere on it that hits it 2 or more times, then when you find its inverse, its reflection about y equals x, it's not going to pass the vertical line test. So the horizontal line test is basically simply a quick check on the original to see if its inverse is itself a function. Okay? So let's take a look at, say, x cubed here, which we're very well aware of as a function. It passes through 0, 0. It's one of our parent functions, up 1 over 1, back 1, down 1. And, you know, I call these John Travolta graphs. Kind of looks like John Travolta in Saturday Night Fever with his hands there, if you know what I'm talking about. If you don't sweat it. But let's say we were to reflect these points now, draw its inverse. Now, I know that if I were to invert the point 1, 1, okay, that is switch the x and y value around, then its inverse will have the point 1, 1 on it, okay, because when you switch a 1 and a 1 around, 1, 1, switch those around, your x and your y, it's the same point. And same thing with 0, 0, and we had negative 1, comma negative 1. When you flip those around, you get negative 1, negative 1. It'll be a little bit more apparent, though, if we were to say, plug in, say, g of 2, we'd get 2 cubed, we get an output of 8. Okay, so 2, 8, which is, you know, clear up here somewhere. That must mean that 8, 2 is also on the graph, so maybe like 8, 2 is like way out here. And what if we plug in, say, g of negative 2? So negative 2 cubed is negative 8. So negative 2, negative 8 was on the original function. So negative 8, negative 2 is on its inverse, which is here. So basically what I want you to see is, you know, its inverse looks like this, and we'll draw it here in a second, and we'll define its function. But yeah, the horizontal line test. Let's go to the original green function here. If we were to draw a horizontal line through it anywhere, it would have struck it only one time in every spot. Therefore, when we find its inverse, when we reflect it about the line y equals x, then a vertical line will only hit it one and only one time. So here's basically the big picture of the horizontal line test. Since a horizontal line never hit my original graph more than one time at any spot, then its inverse is a function because it'll pass the vertical line test. So we'll draw both of these here in a second. I think it'd be good, you know, if we found its inverse function, g of x equals x cubed. Let's find g inverse of x. We want this. So we'll take y equals x cubed, switch its domain and range, so we get x equals y cubed, and to solve this we'll take the cube root of both sides, cube root, and we get y equals cube root x is our inverse function. So in other words, g inverse equals cube root of x. And you know what, I'm having fun with this. Let's go ahead and prove that they're inverses. So what if we found, say, g inverse of g of x? In other words, we took the original output values, g of x values, and plugged it into g inverse. So g inverse would, when we plug that in, we get cube root of g of x, right? Because we put in g of x right here, where we see an x, and x was inside the cube root. We know g of x, that was x cubed, and of course, the cube root of x cubed is just x. In other words, when we plugged in the original output values into its inverse function, we get the original input values, x values. So I said we were going to graph this. Let's go over here. Let's get our parabola out of here. We say, okay, so we had our function x power 3. You know, so here's our original cubic function. We can kind of move this around a little bit here. Original cubic function, but when we graph now g inverse of x, and that was cube root of x, so that'd be x to the power of 1/3 if you're typing it into GeoGebra. Check it out. I mean, you know, it's kind of fun to look at. Basically, definitely reflected about the line y equals x is very apparent. We can pick any point on the original, switch the x and y coordinates around, and you get a point on its inverse. But the point is this, no pun intended. If you pass a horizontal line, and hey, we can actually do that here. We say, like, maybe, well, y equals 3, you know, and I can, oops, I don't want to do that. We can grab that function here. There it is, and we can shift it up and down. That horizontal line would never strike the original function one or more times. And so since that's the case, when we graph its reflection about y equals x, or when we graph its inverse, it'll pass the vertical line test. So since the original passed the horizontal line test, then its inverse is a function. And that's all we want to know about it. Okay? So, hope that helped.